Hello, this is Davidson Potts, and this is Lab 5, Falling Slinky. So, in this lab, we will analyze the motion of the Slinky system and determine the impact of the surrounding on its fall. And we will use GlowScript and Tracker to uh, analyze this situation. So, in this instance, we will be using Newton's second law and Newton's third law of motion. Newton's second law is change in momentum over change in time, and we can use those formulas to get the velocity update formula and position update formula. We've seen this everywhere in the class. And then Newton's third law is an equal and opposite force, which we'll see with the spring system to Earth in an extended system where a collection of particles or objects with masses and positions instead of it being only focused on the center of mass. And the drag force is the resistance force caused by the motion of the body through a fluid like air, in which we will be considering this in this instance. So although it appears that this defies gravity, the bottom of the spring remains stationary because it's at equilibrium, and the top of the spring and the center of mass are at G until it reaches the bottom. So the tracker initial conditions, we're going to assume the system is the spring itself, and the surroundings is Earth, the work done by Earth. The mass is 0.218. We calibrate it to the height of this male. The position is initially set at this position according to the calibration of the tracker in the grid system, and it's at rest, so the initial velocity is 0. And so we can see that the spring stays stationary from 0 to 5.267 seconds until it makes contact, and its final Y position is negative 5.16 times the negative first meters, and essentially it goes into fall after that, free fall until 8.167 seconds. And you can see the position movement down here at the graphs. So we use that data from tracker to plug in here. Basically, just have the G, the value of G, and then the J hat vector is the direction of G in this instance. And then we have to use trial and error to find the constant of drag force. So, so this split into two while loops. And the first while loop, bottom of the spring remains stationary. So in this instance, it's up until the 5 seconds that we talked about before. And the whole time, you can see that we have to use the position update and velocity update formulas here. But nothing really happens. The net force is 0. So Earth is always acting down on the Slinky, but the Slinky has an equal and opposite tension force that we saw due to Newton's third law. And that is Newton's third law. And that force of the Slinky is just a tension force, essentially. So the second while loop, the bottom of the spring remains stationary. It's no longer stationary, and it's in free fall. And so F net is no longer 0. And we go up until the 8 seconds from the 5 seconds. And now we actually have to account for drag and the force of gravity in this instance. And now we can update the position over time and the velocity. And then we plot it on a curve, and these are results. So you can see the predicted model versus the computational model. It's very, very similar. But in reality, there is some error that creates a difference here. So the tracker center of mass can have a small margin of error and discrepancy between each distance and each frame. It was a slow motion camera at like 300 frames per second or so versus us having this many frames or so. And then so there's work done by external forces that we don't even account for, such as wind, even though we're accounting for things such as drag. In a real world, there are many things that we can't consider in this instance. So the initial conditions were also assumed. We assumed that the height was of an average male at about 5'8", and the weight of the Slinky, we took an average there. And then the drag force is done by trial and error over and over again until we see realistic conditions like this. So why does the bottom of the Slinky remain stationary? So when a Slinky is dropped, its center of mass, when we talk about in the extended system and the point particle system, with a constant acceleration due to gravity, just like any other object. So the bottom of the Slinky remains stationary initially because the tension of the Slinky balances the force of gravity. And so apparently the apparent floating that you're seeing is due to the compression wave traveling up and down the spring, back and forth, and then it finally takes time, and then it finally reaches and hits the bottom, and this allows you to experience the net change in force. And so What if there was an object attached to the bottom of the slinky? Would it also remain stationary? Well, so if there's no forces on it, it moves at constant velocity. So it is possible that tennis ball is moving down very slowly, but that would be because of you dropping it and nudging it a little bit downwards rather than just releasing it from your hand. So it'd have a slight downward velocity. But the thing is, it does not slow it downward. That's just the initial velocity. And so adding more weight increases the force on both sides equally, and it still is going to remain stationary. Thank you.